Today, I have the pleasure of introducing the first ever Paul Cristiano Distinguished Lecturer in Engineering here at Carnegie Mellon. Paul Cristiano was the Provost of Carnegie Mellon University from 1991 to 2000. He was an exceptional educator who fostered the growth of cross-disciplinary and interdisciplinary education and research. He also established the Technology-Enhanced Learning Lab to assist faculty in their use of technology to improve the education process. He was a thoughtful decision maker with the innate ability to balance the needs of students, faculty, staff, and alumni. And he has shaped Carnegie Mellon University as we know it today. I worked with him. He was a great colleague and mentor. For our first Paul Cristiano Distinguished Lecture, we have a special guest joining us. Noreen Cristiano, who is a Carnegie Mellon alumna herself, is with us today. Noreen? Noreen worked alongside her husband to maintain the connection of Carnegie Mellon alumni to the campus, and it's truly an honor to have her with us today. Welcome, Noreen, to this special occasion. The speaker today, it's only fitting that he was a student of Paul Cristiano. James H. Garrett earned his bachelor's, master's, and PhD degrees, all in civil engineering, from Carnegie Mellon. He joined the faculty in 1990, and today is the Thomas Lord Professor of Civil and Environmental Engineering and the Dean of the College of Engineering. Dean Garrett's research and teaching interests include the applications of sensors to civil infrastructure condition assessment, data mining, machine learning techniques for infrastructure management problems, and knowledge-based decision support systems. He has published his research in over 60 refereed journal articles and over 80 refereed conference papers. He was awarded in 2007 the Stephen Clements Award for Systems Research at Carnegie Mellon, the 2006 ASCE Computing and Civil Engineering Award, and the ASCE Journal of Computing and Civil Engineering Best Paper Award in 2001. Please join me in welcoming Dean James Garrett for today's.
Thank you so much, Ilker, for inviting me today. What I'd like to do is start off by, again, recognizing and thanking Noreen for being here. It's a great honor for me to be giving the inaugural Paul P. Cristiano lectureship. Paul, as you mentioned, he's a true Tartan, has had an impact in so many ways and in so many directions at Carnegie Mellon. And as you mentioned, I had the good fortune of having Paul as an instructor, and I also had the good fortune of having Paul be the dean that hired me back to Carnegie Mellon, and for that I'll always be grateful to him. Thank you, Noreen, again for being here. Paul had just a fantastic impact on Carnegie Mellon. So what I'd like to do today is take this opportunity. I know this group probably knows a tremendous amount of information about the School of Computer Science and the Tepper School of Business. I'm going to take a little bit of the speaker's prerogative and brag a little bit about my own College of Engineering for a few minutes, so I hope you'll bear with me. Then I'd like to talk about an initiative known as Metro 21 at Carnegie Mellon University, and it's essentially our efforts in smart cities that builds on at least almost 2 decades worth of activity in this area of applying computing and sensing and data analytics to infrastructure. And that gentleman right there Maher Hakim happens to be my first CMU PhD student, and we were working on some of this activities back then when he was a PhD student as well. And then finally, I will talk about some specific applications that we're doing around this smart cities area to sort of bring some specific examples to what we're talking about. So I'd like to start off with the College of Engineering and the vision. Certainly, like every college at Carnegie Mellon, we seek to be a world-class college. We are seeking to be recognized for our excellence, innovation, and most importantly, the societal relevance of the activities that we undertake. And in doing so, our mission is to essentially create very strong, talented, and creative engineers and work on global solutions to the challenges that face society. And we do that by trying, like all of our colleges, working across the various disciplines. And we've really made it a goal to not just work across the sciences or between computer science and engineering, but across all of the different colleges and disciplines that are relevant to the social challenges that we're taking on as researchers. I'm going to brag a little bit about the college. This is something I think Paul would be very proud of, that the College of Engineering remains firmly entrenched in the top 10 U.S. News and World Report rankings, 5 at the graduate level and 6 at the undergraduate level. Many of the programs also at the individual level remain very highly ranked, and some are very close to making their way into the top 10. This is one that we're all proud of, that we're getting recognition by women for the College of Engineering and the great environment in which we offer. And so the thing I'm proud of is at the undergraduate level, we're approaching 40% women. And Noreen will remember when Paul was an undergraduate, you could count the number of women probably on one hand in engineering. This is the competitive environment in which we in the College of Engineering exist. And our provost is from Michigan, and Michigan is right on our heels in terms of rankings. And we have MIT, Stanford, Berkeley, and Caltech in front of us. And so it's a really tight field, very strong competitors. The college overall has grown. It currently has about 1,800 undergraduates and nearly 2,000 graduate students. About 4 or 5 years ago, the number of graduate students surpassed the number of undergraduates, which at most of the premier private institutions, that's occurred. And so it's happened at Carnegie Mellon as well. We have about 140 tenure-track faculty and about 80 research, teaching, and special faculty. And the reason I bring that up is, again, come back to the rankings. And one of the things I'd like to show is the sort of the energy density that we have in the College of Engineering, the impact that we're able to have. If you look at the numbers of faculty and the rankings, you see that only Caltech and Carnegie Mellon have smaller faculties but able to maintain high rankings. It's quite a valley in which Caltech and CMU exists, and it remains a very big challenge for any dean of this college to be making investments, using the resources that we have as efficiently as possible to be able to compete against much larger colleges of engineering. So some of the areas in which I'll highlight a little bit of research activity, and I am going to talk about this whole smart cities infrastructure area in more detail, so I won't really talk about it here. And the first one up in the upper left corner, this additive manufacturing area, I won't talk too much about that either because my colleague Gary Fetter will be talking about that tomorrow. But additive manufacturing is an area that we're making a big investment in the college and at the university. And it is, in fact, going to be a transformational technology that will affect supply chains. It will affect manufacturing as we know it. It will have a tremendous impact across a number of different application domains. So what I'm showing here is a skull with implants that have been additively manufactured for the particular context of that particular individual. They're very lightweight, very strong, and can be seeded with biomaterial that allows them to be inserted and provide healing rather rapidly. We also have the ability to additively manufacture parts with an extreme amount of detail, and it actually can be done with no greater effort than a part that has much simpler details. So designing in an additive manufacturing environment is going to become also an area of study for the future. We have a major research activity in cybersecurity, which I know is well known here. SURTQ or QCERT is, has been an activity here for quite some time. I point out here the work by Mario Savides in biometrics, looking at facial recognition and pulling facial features out of very fuzzy images so as to be able to recognize people in a very dynamic and highly accurate manner. And then finally, we have a tremendous number of new faculty in the biomaterials and biodevices area, working on everything from an artificial lung, artificial limbs, robotically controlled artificial limbs, devices that can be swallowed and essentially collect a large amount of information as they pass through the body. And then some of these faculty are bioprinting vascular networks on their way to creating artificial hearts and, or in fact, artificial heart patches that can be used on top of the actual human heart to be able to address certain heart ailments. Other areas, just to make sure that if my colleagues are looking at this video, I don't get myself in trouble. There are many other areas of expertise that we have, and I just simply, out of time, aren't able to talk about them, but we have a major amount of work going on in nanotechnology, and we're about ready to launch an 11,000 square foot nanofab facility back in Pittsburgh that will, again, give us a tremendous boost in terms of our ability to work in that space. As dean, I also like to point out where we're making additional investments in the college. It was pointed out in Ilker's comments that Paul was very much instrumental in getting technology-enhanced learning as a concept started at Carnegie Mellon. And I'll say that as dean, I'm making an investment to try to have more and more of our courses be technology-enhanced, meaning we're not necessarily doing MOOCs, but we're trying to have a lot of the courses have digital capture of the videos and make it possible to interact through digital interfaces. That helps us as we have our international locations in Rwanda, Silicon Valley, China, and Portugal take advantage of the engineering courses offered. In addition, working with Gary, before Gary took his position as Associate Provost for Research, he was the Associate Dean for Research, and he and I put in place some significant investments in equipment grants, seed funding, and some space that, again, is going to be is located in Scott Hall to accelerate research activity within the college. Another major area that I hope you're seeing, because I know Ilker's doing the same thing, making investments in marketing and communications that helps get more of what is going on in the College of Engineering out into the national and international forums. And then lastly, I made an investment in a Center for Faculty Success that helps prepare our young faculty to take up the business of being a researcher much more effectively than we have in the past in terms of providing programming, providing mentoring, and actually the center is helping us to change our search processes as well for hiring future faculty. What this graph shows is the locations where the College of Engineering has campuses and has programs. You'll notice it doesn't show Qatar. It's not out of disrespect for Qatar. It's just that the engineering college does not have activities here. But we do in Portugal. We are part of the CMU Portugal program, along with the MIT Portugal program and the UT Austin Portugal program. It's a significant activity with up to 15 different Portuguese universities and other institutes, and over 20 departments at the university are involved in this Portugal program. So it's not just the College of Engineering, but we manage it for the university. We have a new but significant activity in Rwanda to provide MS in Information Technology and MS in Electrical and Computer Engineering programs. We graduate about 25 students per year, and we're hopeful that that will grow to 50 students per year fairly soon, and in fact attract students from all across sub-Saharan Africa. And we also have a large program and interaction with Guangzhou, China, at Sun Yat-sen University in Guangzhou, and are educating about 50 master's students per year in that program. Now I'd like to switch gears and talk about this Smart Cities initiative, which we've referred to as Metro 21. A small story about the name is that we started to call it Smart City 21 or City 21, and the county executive got quite upset with the use of city and not referencing the larger surrounding metropolitan area, and so hence the name Metro 21. It works for us, and it's a little bit more inclusive. So what is a smart city, or what is smart infrastructure? Well, first of all, you need to start by thinking about what a city is. A city is an interconnected collection of support systems for the citizens that occupy the city. You have a large number of different infrastructure systems for transport, for electrical power generation and distribution, for water and wastewater treatment and distribution. So that's one class of systems. You also have lots of buildings for different uses, certainly government, corporate, industrial uses, private usage. And then finally, you have many different public services that interact with the built environment and other transport and electric generation and so on. My definition of a smart city is one that essentially uses a large amount of sensing, data collection and integration, data analytics. Data analytics are extremely important in this whole smart cities concept. And then in addition to just analyzing the data, you try to put that data into predictive models that can be used for identifying when there may be problems associated with a single infrastructure system, but more importantly, when you can start to identify problems between the interacting systems. So if you think of a city as a system of systems, what you're trying to do is collect data about how all these systems are operating individually as well as how they're interacting with each other. And so the concept will be that by doing this, by capturing this information and being able to predict the performance of these different systems and their interactions, that you'll actually be able to improve the quality of life of the individuals by removing disruptions, by removing unexpected outages of all these different systems that are so much needed for the citizens of a city. And as you get more and more people occupying cities, this ability to operate the cities in an efficient and effective manner is going to become all more important. We've recently experienced a water main break that our own provost was the one who discovered on the campus, and it took him driving around at 10 o'clock at night to be seeing a massive geyser in the vicinity of the Heinz College. That shouldn't be the case. It shouldn't take that we have to rely on our provost to be identifying water main breaks. This should be something that we know ahead of time is likely to happen and that we proactively address instead of waiting for the reactive situation. It's still, well, it just opened almost 3 weeks later after the water main was discovered. So why do we need smarter infrastructure? That's one example. The other is a pretty serious example of the collapse of the I-35 bridge. That's a really extreme example of what can happen if we don't pay attention to our infrastructure systems. But the idea is that the U.S., just the U.S. alone, and this translates across the globe in a more significant manner, but just in the U.S. there's trillions of dollars of built infrastructure. And by that, bridges, highways, dams, pipelines, and so on. And the U.S. condition of that, or the condition of that infrastructure in the U.S. is pretty significantly degraded. The American Society of Civil Engineers grades that infrastructure to be, at best, on average, around D+. We would be quite upset with any of our kids if they were bringing home a D+ average on what they were doing. So, and the ASCE estimates that about a 5-year cost of bringing that infrastructure up to not even perfect condition, but reasonable condition, is in the trillions of dollars. And so this amount of money is not going to become available. I can guarantee you that. So what we need to be thinking about is how do we use technology to, in fact, avoid that kind of cost for replacement and repair and be able to more efficiently and effectively operate our infrastructure. So we need to gain traction on the state and condition and operation and management of infrastructure so as to be able to better manage the infrastructure that we have. The idea is that smart data-driven maintenance will in fact save money, it will save disruption, it will save all kinds of collateral costs that come. So imagine again that water main break that Farnham discovered. If we could have been able to know either that when it was just breaking, what valves to shut off, what emergency responses to call in, we could have mitigated a tremendous amount of damage. And then the other thing is three weeks of disruption of a main thoroughfare through the city causes people to avoid that part of the city. Economies are affected, and so on. Just as a data point, a robotics company in Pittsburgh that started out of Carnegie Mellon called Red Zone, they essentially provide technologies for videotaping and maintenance of sewer systems. And their data point is if you can proactively manage a sewer and avoid a sinkhole or some other problem caused by a damaged sewer system, you will avoid 2/3 of the cost that you spend when you're dealing with it in an emergency fashion. And any of us who have had a water break in the house or have had some sort of an emergency know that you're spending lots of money very quickly and you're seeing lots of damage while you're trying to deal with something, as opposed to if you proactively plan and do it in a manner that you can control the damage, you save a lot of money. And this is the idea, I think, behind smart infrastructure, is by using sensing and analytics and predictive modeling, you can really avoid a lot of disruption and cost. Okay? So I think I just basically said this. So in summary, the smart infrastructure blends this concept of traditional built infrastructure, which we call the built environment, with cyber infrastructure, meaning computing, sensing, networks for collecting all that data, and then all of the data analytics that I think our colleague Andrew Moore was through here recently. I'm sure he was talking about, machine learning, data analytics, data mining, and artificial intelligence. You start to combine these technologies together, and you have what we refer to as smart infrastructure. And the idea is that you'll be able to save money, save energy, save disruption, and that's the key behind improving the citizens' quality of life within a city, just specifically related to infrastructure. Now let's talk a little bit more about the Metro 21 initiative. It's not just about infrastructure, it's about the larger set of services and interacting systems that make up a city. So we have the Smart Infrastructure Institute was one group of researchers and activity in infrastructure. we have had a tremendous amount of and long history of work in autonomy and autonomous vehicles. It started in the School of Computer Science and now is very active within the College of Engineering. And so that activity is very much a part of our interest in the Metro 21 initiative. And then the university, within the last 3 or 4 years, received a University Transportation Research Center from the Department of Transportation focused on vehicle-to-vehicle and vehicle-to-infrastructure communication for improving the safety and efficiency of transportation. And so the research activity in that space, combined with the autonomous vehicle work and combined with the Smart Infrastructure Institute, is what is forming this Metro 21 activity, plus a lot of interest in bringing in social science and the policy dimensions, so we're working with the Heinz College as well. So the Metro 21 initiative actually involves 5 different colleges: the Engineering College, the Heinz College, directed by Dean Krishnan, who will be here next week and talking more about that dimension of the Metro 21 initiative. And then, of course, computer science is very active in this space. So is our Dietrich College. The Dietrich College has social and decision science. It has statistics. It also has folks in psychology that are relevant, because if you want to start to change decision makers, you can't just provide them data. You've got to understand what kind of data is going to drive people to make different choices. And then we have the College of Fine Arts through, is Ramesh here? I saw Ramesh. Anyway, the College of Fine Arts has both architecture and the urban development folks that are part of this initiative. So the big picture is to affect a large number of cities by doing some basic research in a variety of test beds that are live and helping to illustrate to cities what the impacts of this smart cities research and technology can be. So let me walk through this graphic a bit. Is this? I think this is it. There we go. So down here are the basic research areas that are very relevant for Metro 21. We have sensing, of course, all sorts of different types of sensing. Gary's work in microelectromechanical systems has been instrumental in creating ubiquitously available accelerometers and so on. And that kind of sensing is one example of the kind that we use in the smart cities area. Communications that helps collect and share all this data that's going to be collected in many different contexts. The predictive analytics that I talked about, that's taking all this data and being able to develop models that will be predictive of how a system will react to environmental conditions, will react to other systems influencing its behavior. So if you have an interaction between air pollution, intersections, and various sources of traffic, knowing how those systems interact with each other and what happens when to the air pollution when you maybe adjust the traffic from one area to another will be important for understanding whether you should do that or not. Finally, this whole area of connected automation allows for the robotic nature of what we're talking about. It's one thing to collect data, to do analysis and then be predictive of a problem, but you need to have the connected systems to be able to act on that data and make changes in real time. So if you think about it, what we're talking about with smart cities is also a very strong robotics concept. Robotics is about sensing, thinking, and acting, and what we're talking about in a smart cities context is that ability to sense, collect the information, think about it, and then act. And in addition, in this case, we have an additional dimension that we have to worry about, and that's privacy and security. Because as you start to collect all of this data, you really very quickly get into privacy issues as you are able to identify where individuals are, what they're doing, and how they're interacting with all these various systems. That then leads into a whole variety of different test beds that we're interested in. We're interested in safe infrastructure. We don't want pipes breaking. We don't want bridges failing. We don't want dams failing. We are interested in safe and efficient transport. We want people moving over these infrastructures to not to be avoiding death on the highways. There's some estimates that when we do affect all of these technologies that we're developing for vehicle-to-vehicle and vehicle-to-infrastructure communication and autonomous vehicles, that we're actually going to see a 90% reduction in highway deaths. And so that is something that's quite exciting and will have a tremendous impact on our society. Utilities are another area, certainly smart meters for electricity usage, smart grid technology is something that's a relevant test bed here. And then finally, the environment. As you're able to use these technologies to reduce energy and reduce costs of operation, you will, in fact, reduce various forms of pollution as well. And then finally, the vision is to not just do this in Pittsburgh and not just to do this in the United States. These are all obviously U.S. cities, but the idea is to learn from different organizations and different research universities that are working in different cities and provide a worldwide laboratory of the research that's going on in these different cities. And in fact, take something that's working in San Diego and provide it and try it out in Pittsburgh and see whether it still works or not. There's a tremendous amount of research opportunity here just to look at what's happening in each of these different cities and the challenges they face and how that affects the application and uptake of these various technologies. So another dimension of this that I haven't mentioned, I mentioned Metro 21 is the Carnegie Mellon initiative for looking at smart cities technology. We also have established or helped to establish a Metro Lab network, which is 20, I think now we're at 25 different cities and local universities in those cities that are working on smart cities technologies. And this Metro Lab network has been established by the Office of Science and Technology Policy in the White House to, in fact, cause a greater amount of sharing and a greater amount of collaboration in this space within the U.S. So the purpose of the network is to promote this city-university partnership and to promote a successful set of research activities and deployments within those cities and develop a platform by which cities and those universities can share their results across all these different cities. These are the different cities and the local research universities that are part of this Metro Lab network. As I said, it was started by the White House, but Carnegie Mellon has been tapped to be the director and the maintainer of this Metro Lab network, and our Metro 21 initiative is the host initiative for this activity. So now let me, how much time do I have? 15 minutes? Okay, so let me talk about some of the projects and that are a little bit more specific to give some examples. The first is one that's near and dear to my heart. It's the idea of using vehicles that travel over all forms of roadways, railways, and so on. Use the accelerations that are collected from vehicles over time and in different contexts, different environmental conditions, different traffic conditions, and use that as data for assessing the state and condition of infrastructure. So right here I show a bridge with vehicles driving over it. Each vehicle does already have accelerometers in it, and if you can capture that data and develop patterns over time, you can begin to understand whether there is or is not a problem that's emerging within that infrastructure. Now, to make this real, we actually put accelerometers onto the light rail transit system in the city of Pittsburgh and have been doing so for the last 2 years and collecting acceleration data from that vehicle through all the trips throughout the day that it's making around the entire network. You didn't know, Noreen, that the light rail system that comes out to the South Hills has these accelerometers on it from Carnegie Mellon. But the idea is to acquire the data, do a tremendous amount of signal processing on that data, and begin to identify changes in that data over time, and show that data to the maintenance folks on the light rail system, and have them identify very rapidly whether something is appearing to be an anomaly or whether it's potentially an artifact of the sensing that's going on. And an example, this is the entire extent of the track for the light rail system, and or a section of the track of the light rail system. And what I'm showing here is this is before a maintenance activity was performed. Where the maintenance activity is to essentially lift the track, tamp down the ballast, and essentially smooth out and improve the track. And what we were trying to do was to see if the accelerations alone that we would collect before and after that maintenance activity would illustrate the change in the condition of the track. And in fact, what this third graph shows is the difference between the before and after, and the correlations between the accelerations before and after. And what you can see is we actually do detect, using this particular approach, where there was a change in the condition of the track. And doing that, we would be able to use this kind of a technology in the future to identify proactively where there appears to be an emerging change in the condition of the track that could then be a focus of the maintenance activity. Too many times in infrastructure systems, it's scheduled maintenance. They go out and do something in a particular part of the track, whether it needs it or not, and they're potentially wasting large amounts of money fixing or trying to fix track that doesn't need to be fixed, and in fact ignoring other parts of the track that could deserve attention. Another example is the work being done by Christoph Mertz in the Robotics Institute. The idea here is to use very inexpensive visual technology, cameras and on iPhones, in fact, and to capture all the different changes in the road conditions, potholes, and you don't have any potholes here, right? But we have lots of potholes in Pittsburgh, and so they're basically using this onboard video camera to just capture what's going on out in front of the vehicle, collecting the data from that dash cam all on both sides of the road as to what is the state and condition of the road, and then aggregating that into a map of all of the conditions of all the roads, showing, green is where there's no damage, red is where there's a tremendous amount of damage, and that can again help focus the maintenance facilities on the places that need it and not necessarily fixing parts of the roadway that are less damaged. Another really exciting example is, I think, relevant here as well, this idea of using cameras and artificial intelligence reasoning to better manage networks of intersections. Not just, you can see intersections that have loops and abilities to control the lights, but those are still point to point. They're not taking into consideration all that's going on in the system of intersections. And so Steve Smith in the Robotics Institute developed this technology called Scalable Urban Traffic Control, or SURTRAC. It's now a company, and it's actually being deployed in the city of Pittsburgh to essentially better manage the throughput of intersections over a larger network of those intersections. And what happens is when you do that, when you're essentially using the cameras to collect the information across, maybe 50 different intersections in a region, you can think about how to affect the lights in a way to get a maximum throughput and not do it point by point. Now, you might be an individual sitting at an intersection thinking, man, this is a stupid light because I'm sitting here forever. But what's happening is more people are moving through the intersection because you're maybe individually waiting, but more people are actually being supported. And when you do that, you see reductions of 40% in vehicle wait time overall, reductions of nearly 26% in travel time, and a little bit over 20% in vehicle emissions. These are significant results for this test bed that was applied within the city, so much so that the mayor, Peduto, was excited by this work that he wants to, in fact, have all the intersections within the city of Pittsburgh be dealt with this kind of technology. Some other project examples, again, I won't dwell on these because I'm running out of time, but we have people looking at putting sensors on pipelines to be able to detect before a gas explosion would happen, the beginnings of a problem within a pipe. You might get reduction of the thickness of the pipe. You might start to have a crack show up in a pipe, and before it explodes, you would be able to actually detect that. We have drones being used for detecting information from bridges. We have faculty in electrical and computer engineering that are using speakers to localize people within a building to better be able to manage where people are and where people aren't within a facility and not have to install a huge amount of expensive sensing to be able to do that. Finally, a colleague of mine, Borchua Kunja, is embarking on a project to use air pollution or air quality measures as a means to detect potential leakages in gas pipelines. And we did a similar project a number of years ago around water main breaks. If you could start to understand what might be causing water main breaks to show up in greater frequency in certain areas, you could start to be predictive of where you might see that same set of conditions elsewhere in a water distribution network, and then proactively go in and replace more of that pipe in that area, and not just wait till a water main break happens, replace it locally, and keep chasing these breaks. So, in summary, just want to remind everybody that the U.S. alone has trillions of dollars, and I can't imagine what, if you start to add this up worldwide, the extent of the infrastructure that's been built. We're seeing a tremendous amount of infrastructure being built here in Qatar, but you're not experiencing the problem that the U.S. is in terms of now having to maintain that large amount of infrastructure. In terms of traffic, you see it, but what I mean is you have other infrastructures that are still fairly new and not showing the kinds of breakage behaviors that we're seeing. We have to start collecting data on these infrastructures and using that data to better manage it. If we do so, we'll be able to improve the quality of life of the citizens, avoiding unnecessary expense, avoiding unnecessary disruption. And these smart city initiatives in this, in Pittsburgh, but certainly almost in every major city is starting to look at this. These are going to provide a tremendously rich number of research opportunities, as well as a chance to have a major impact on it's one of the global impacts that we in the College of Engineering seek to have through our research. So thank you for your time. If time allows, I'd be happy to take any questions.
Thank you. Great talk, Jim. But of course, I'm biased because you're one of the few people who shaped my life, and I will never forget that. But my question is, when I go to industry conferences on smart cities, they always devote as much time on things you've talked about with smart infrastructure, and they devote equal amount of time to things like citizen engagement, crowdsourcing, shared economy. You can't go to a smart city conference without having Uber and Waze talk about what they do in that. And that was missing from your talk. Is it because you're taking the engineer perspective on smart city, or?
Yeah, that's a very good question. It's because my perspective is I've been working in civil infrastructure and taking that perspective, and because this is a talk, I wanted to go into some technical detail and not just have it be dean speak across the entire length of the talk. I went into that direction. But you're right, Maher, that in fact it's why we have to get the Dietrich College of the Humanities and the social and decision scientists involved and the sociologists involved in this as much as the technology. In fact, I think we're way out ahead of in the technology space. What we need to do is be looking at, it's one of the reasons why I would love to get the Tepper School more involved too, is we have to look at new business models for how this would work. Society is going to be asking, why, why do we need to pay for this all up front? Why can't we do this in a more, amortized way? That's an additional dimension I haven't even talked about. But you're right, the social dimension is very important, and in fact, I will hope that Krishnan will very much talk about that dimension when he comes next week. Is it next week that he said? Yeah. Sunday. Yes?
Seems like a lot of what you presented can be predicted, or some of what you presented, I should say, could be predicted from very detailed local weather information. And I'm wondering, to what degree is there a trade-off between prediction and censoring?
I'm glad you asked that question, because I actually do not believe we should put any sensor out there that is the data can be collected from some other more ambient approach. So in other words, my idea about, or our idea about using vehicles as a sensing mechanism for a very large amount of infrastructure is akin to your saying, if I can do this with weather prediction, why deploy sensing? I'm agnostic to whichever type of sensing gets put out there, as long as we can show that data that you're talking about is predictive of the behavior that I'm looking to predict. And that's where I think we're going to see a tremendous amount of opportunity as the data analytics have gotten so sophisticated in recent years, and the data that's being collected and reported publicly is also becoming much more voluminous. And so we may not have to put sensing out in certain application domains because the data is already there. We just need to see it, understand it, and apply it. Yes?
I'm not sure if any of your smart city project ever talking about this. A couple of years ago, one of my former students who supervised a group of Taiwanese students won the first place in a smart city creative competition in Germany. They proposed installing RFID on every intersection of the city to help blind people to go home. Since this kind of project doesn't create revenue for society, for government, but do you think would that be realistic for U.S. government to do that?
My sense is I think it does bring value in that you allow a greater diversity of people that can live within a community, they can contribute to the economy, they can be part of the workforce if they're able to have the mobility that you're talking about. So that's one thing. What I want to always be careful about is sort of at this particular point predicting a particular technology being the means to provide that mobility that you're talking about. RFID could be one mechanism. Certainly, we're seeing the ability to localize by other technologies. Again, ambient speakers are able to localize people within a building. You may not have to, in fact, deploy RFID tags at these intersections if, in fact, you have cameras that are already there for the purposes of controlling vehicle traffic through the intersection. They may also be able to pick up any human in that intersection and then be able to relay that back to the person's cell phone. So you might not even need that technology. That's the thing we have to be careful of as these concepts are emerging, that we say too quickly focus in on one particular type of technology. That's why I think this Metro Lab network concept is really exciting, that you can have one city trying RFID tags, another city trying cameras, and a third one maybe trying triangulation using speakers, and figuring out which technology is the most effective. But I think it's a great application. It's a great use case. The technology may still be up for grabs. Yes, sir.
Is anyone studying the organizational implication of all of this? Who's going to orchestrate this?
Yes, that's a great question. It's one that I think is, again, wide open. I do know that there are some studies on that, because they're trying to understand how do cities uptake this technology. how do you take this system of systems in a city? They're all stovepiped right now. You have the Public Works Department is in charge of one set of infrastructures, and they protect their data pretty strongly. What we're starting to see in these cities that sign up to be part of the Metro Lab, part of the commitment is to open their data up. And so I think there will be an opportunity brought about by this Metro Lab network to study the kinds of organizational changes that some cities take on, others don't. How effectively then do certain initiatives get taken up by the city? Oh, yes. Right, right. In fact, new business models are going to have to be needed because right now I think you had some early adopters of technology trying to get cities to adopt it, but they were going to charge them huge amounts of money to have the technology installed, and the cities couldn't afford to do that. Any other questions?
Can you tell us more about the work being done with autonomous vehicles and how smart cities might interact with them in the future?
Oh, sure. This whole University Transportation Center that I mentioned, it's called TSET, Technologies for Safe and Efficient Transportation, is looking at technologies about, you have connected vehicle technology and you have autonomous vehicle technology. Okay, so connected vehicle technology is that there are humans in the driver's seats, but their vehicles are communicating their relative locations. They're predicting whether there's an impending collision and trying to avoid that. And then you have autonomous vehicles, which true autonomy means they're sensing their entire surrounding environment and making all decisions purely in an individual unit basis. So the direction that this research is looking at being led by Rajkumar, who is another person that you should get to come and do a talk. He's leading both the Metro 21 and the University Transportation Center initiatives. But he's trying to combine this idea of connected vehicles with autonomous vehicles, and then you have a connected autonomous driving. This is where you'll truly gain a tremendous amount of both safety and effectiveness of autonomous vehicles. The idea is behind autonomy, the idea of autonomous vehicles is that you can run them in a tighter headway and in a much greater density and at a higher speed. And therefore, you can make much better use of the existing infrastructure and not have to continue to build more and more highways and more intersections and more infrastructure. Did I answer your question?
One more question.
Good. Thank you very much. Appreciate it.